Hi, friends of the sun. Welcome to our reading group. It happens every Monday, and we just have an author of a paper here, talk with them about their paper, or just chat about the paper ourselves. And you can suggest papers or join the Zoom calls that we have about the papers yourself, with all the information that's down in the description. And today we talk about the paper called Diffusion Forcing from Boyuan Chen and Vincent Sitzman, some MIT people. And it's kind of similar to rolling diffusion, in case you've heard of that. And yeah, I think many people have been thinking about stuff like that in the context of video generation. And here in this paper, we also look at like trajectory planning and solving mazes, stuff like that. And yeah, maybe this sort of stuff and line of research will be useful for video generation pretty soon. All right, let's go.
Hi everyone, I'm Boyuan Chen. I'm a rising fourth-year student here at MIT ECS, working with Professor Vincent Sitzman and Professor Ross Drake. My main research interest is foundational models for decision making and like word models, especially video word models. And I will introduce what I eventually want to do, like in the next presentation, and then I will talk about my recent paper, Diffusion Forcing, Next Token Prediction Meets Full Sequence Diffusion. It is a really popular paper, at least from Twitter, and I'm really excited about it. And we are already working on like many follow-ups on this. Yeah. So I guess I will start my presentation. Hannes, can you remind us about like how much time do we have for the slides alone, excluding questions afterwards?
Basically as much as you want.
Okay, cool.
Okay, so also Boyan, I'm gonna leave this to you mostly. So I might have to drop out in the middle as well. But yeah, that's good.
Yeah. Okay, let's begin. So let's talk about our paper. But before that we dive into our paper, I want to make sure that people are on the same page with me on the big picture. So what do we want to do eventually? So 100 years from now, everybody would want to see intelligent robots that perform their daily household tasks, like robots that cooks for you, robots that like do all the dirty laundry for you. And that is a big picture. And to power those robots, you need intelligent AI that can help them model the physical world. And by modeling it in the physical world, I mean, it's like a model as general as the large language models right now. You can just prompt it to do anything and it will actually do the task for you. And we want to do it in a fully self-supervised way. That is, we don't need to hire billions of humans like teaching those robots. We want to do the interesting part, that is self-supervised learning, and let them learn the skills from what we have already. So when talking about like learning from the physical world, there are multiple ways to do this. So first of all, we humans are generating videos of we doing everyday tasks. So for example, on the left-hand side, we are seeing like this application data set is recording of like people doing all kinds of stuff in the kitchen. And all these videos contain a lot of interesting things about the physical world. Like here, you see the plate breaks, and there's the physics. And you can also see the human hands motions, right? Like how do I pick up the plate properly? So there are other sources like interaction. So you can let robots interact with the physical world, and you jointly record the video it sees, as well as all kinds of actions. I mean, in terms of these robots, I would say like joints through as a like execute the task. And both of these philosophies like follow this sequence generation task. So that is, so in your first data source, you have passive video. That is, you can use a camera to take photos of your image sequence as you execute the task. And then you can imagine that if an intelligent robot, what could it if it can predict such sequences? What we can do is that we can prompt it just like how we prompt large language models. For example, if I want a robot like to open a door for me, and it had never seen this door before, okay? However, it's able to do the sequence generation task. What it can do is like you take a photo of like this door and this door handle, and it can just imagine that how do I open the door by generating a sequence of images containing some humans or like a robot like opening the door, like and including like fine-grained motions of a hand, and then we can later extract that. So on the other hand, if you happen to have action data that is like image coupled with actions, you can jointly like predict your future and like your actions together. And what you can do is like you can directly execute those actions and like generate more data and feed into the data loop. So that is a big picture. Like we want to model the physical world. And one of the fundamental ways is sequence generation. In particular, to me, like for roboticists, it's sequence generation of images and actions. And in fact, we humans treat videos as our input to our eyes. And we model everything from video streams. That is, we have a lot of like 3D visual concepts, like 3D, like motion priors, objectiveness, and they all comes from video. So the form that like you take from your eyes, like raw, you every day like you wander around the world and like you receive the information like from videos, and only from videos you get all of this. So theoretically, if you can model videos, you can model 3D, you can get all the motion priors and like eventually solve objectiveness and all these kind of things. So here what we are building a specific type of like word model here. So we hope that we can, given like current observations, we can like diffuse like what is the action to take from this moment, and we can also, and if an action is specified, we hope that we can predict like what's happening in the future. And basically in diffusion forcing, we're trying to build a better sequence model because we found a lot of current sequence models are unsuitable for the grand goal we want to have. That is like we use like a video word model for decision making. And there are two major paradigms to build this. So first of all, everybody have seen Sora, that is a awesome like video generation model from OpenAI, and they can generate a lot of realistic videos. And on the other hand, there are large language models that everybody already know, ChatGPT, and they are powered by different technical methods. Video generative models, they rely on diffusion models. And in particular, that is what we call full sequence diffusion. That is, I just divide this video like I treat this video as a whole chunk of data, disregard of the structure. I just throw everything into a diffusion model and I diffuse every pixel, every frame jointly. On the other hand, large language models are powered by something completely different that is called next token prediction. That is like to generate like a full sequence. What I do is like I start with the first token, that is a letter I here, and then I generate like I like, and then I feed the I like into my model again and to predict the next distribution of like next word here that is cats. And after I generate cats, I feed all three like I like cats to the language model and I generate again. So by doing this recursive autoregress sampling, I can use this next token prediction model to generate a whole long sequence. So these are the two paradigms.
Sorry.
Yeah. And what we want to do in diffusion forcing is that we invent a model that combines the best of both, and you will know like what is best about them very soon. So there are some preliminaries here. So but I want to propose here, I want to unify both models. And the way we unify them is this intuition called noise as masking. So it is pretty common that when people train language models, for example, from the very beginning, like when people like are doing GPT-1 or like a BERT, like they mask out certain entries in your sentence and like try to train the model, pre-train the model, but predicting those missing entries from the rest of the unmasked tokens. And here, the core intuition is what we call noise as masking. So imagine you have a video sequence here, unmasked, it's clean, free of noise. And then you can add slight amount of noise to these models, creating like a slightly masked version. And then you can also fully mask it. That is like you can mask it with like completely Gaussian noise. Okay, so that is what we call noise as masking. So now imagine that you have these two axes. So that is you have the vertical one is noise axis. That is as you go from the axis, you have fewer more and fewer and fewer information. And on the other axis, you have time. That is like the common like t in along a video. Okay, so what does Sora do? So that is what we call like full sequence diffusion. So look at this picture. Like how we train Sora is like we start from I can't see my mouse, but we start from the bottom of the right of the middle image. Like we first add a small amount of noise to observations here, that is taking all this like gray squares like into blue squares, and then that is what we feed into the neural network. Like we feed this noisy version of images into neural network, and we ask the neural network to denoise it to generate a clean version of that. Okay. Thank you, Hannes. Yeah.
Is that right?
Yeah. So one notable factor is that when people train Sora, people add same amount of noise, same level of noise, like to every token, like throughout the video. That is like your initial frame and last frame, they all have like same noise level. So there are a lot of techniques, like when at sampling time, you have different like different uncertainties, as we will see later. At inference time, what people do is like we start from pure noise, a sequence of pure noise, and we feed that into our model because our model can denoise it. We can denoise it a little bit, then denoise it further until like we reach like a clean sequence. So that is the full sequence diffusion model. On the other hand, we have next token prediction models. That is like at large language models. And at training time, what people typically do is this. So we feed it with like some clean tokens that is like for example, like in the above sentence in the example above, I say like I love cats, right? And one data point that's used to train is I feed it with I love and ask it to predict the next thing, that is cat, and I apply a loss on cat. What is input out behavior if we want to model this in diffusion? That is, I feed it I love, that is clean, free of noise, history, context, and ask it to diffuse the next token, that is cats. So what I will have is, for example, like in the context of videos, it's like I feed it with frame 1, frame 2, that is past observations, that's already known. And I feed a noisy version of frame 3 and ask it to denoise, output the clean version of frame 3, given frame 1, frame 2, and noisy frame 3. And at inference time is pretty similar to what we done earlier. So basically we start from frame 1, frame 2, and now I can iteratively diffuse frame 3. And then after frame 3 is also clean, I can feed frame 1, frame 2, frame 3 into our model as context, and then I gradually diffuse frame 4. Okay, and this is also doing autoregress sampling like large language models, but with diffusion. So you can actually see there are a lot of similarities between the two type of models here, unified by this noise as masking framework. So when you apply noise at a very high level, like if you are only left with noise and there's no signal about original image, then it's essentially completely maxed out. And that's equivalent to like what many people did like in earlier like large language models like masking, except that we are doing fractional mask. That is, we can choose to either apply complete noise that masks everything, or we can apply no noise, that is like you receive the clean image, or you can do something in the middle. As a small amount of noise, it lost some information, but it's not completely lost. I see something in the chat here. Is there a question?
Yeah, it's just, is it known that Sora is a full sequence diffusion though? Like it's not something also halfway autoregress or something like that.
Yeah, I think so I think people don't have full answer on this, like you work at OpenAI, but like from what people says and what from like what everybody talks about, like it's like a DIT. It's full sequence non-causal DIT.
Also, I mean, Sora is just one example, right? So there's like the runway model, or there's the Luma model. Actually, in fact, on the slides, it's the runway. It's actually the runway model. I realized we forgot to include the citation. But yeah, my understanding is that I think even for the OpenAI Sora model, they talked about it. They talked a little bit about the architecture, and I thought it was a full sequence diffusion model. But yeah, not 100%.
Yeah, and by doing this, like you can do a lot of things. So for example, like you can do video prediction, as we saw. Like maybe you can like do language as well, which we didn't explore yet. But overall, like sequence generation can do a lot of things. However, there's one particular beautiful thing about diffusion, that is the ability to do guidance and like planning. So for those who don't know, like guidance is unique capability of diffusion models. That is, at first you can just train diffusion models like on a bunch of like unconditioned images. That is like maybe not sorry, I'm talking about specific type of guidance called classifier guidance. And the way classifier guidance work is that you can train your generated model on a set of like unconditioned images. That is a mixture of like every single class, like dog, cats, everything. Okay. Now imagine at test time, you only want to sample pictures of animals, and you only have access to this unconditioned, like every class, like generated model trained by diffusion. There is a unique ability of classifier guidance. That is, if I have a classifier telling me whether an image is an animal or not, I can combine it with the existing unconditional diffusion model, and I can like generate samples from that particular class only. And that kind of ability is also useful for planning here. As you see, like here, we're trying to generate a sequence that goes from a start to a goal. Okay. And we can use this ability of guidance to do this planning task. And it's really useful. So imagine that like a good trajectory here is like we have a classifier about what is a good trajectory and what is a bad trajectory, right? And imagine that like what the data I see is a lot of like bad trajectory, good trajectories mixed with bad trajectories. And here at test time, now I have a specified particular goal and like a start in my mind. And what I want to do is generate a sequence that goes from goal to start, from start to end. And what I would do is like I have a classifier, let's say like a reward or something that tells me like whether like generated trajectory is good. And then I can guide the sampling such that it only generates trajectories that give me high rewards. That is a legit path that leads from start to goal.
So where does this where does this now fit in with the like if you have a sequence, maybe this is the start of your sequence and this is the end of the sequence, then yeah, where does now the guidance with like a classifier or like a reward function fit in?
Oh, I see.
In the
So
framework of like, right, it's clear if we do full sequence diffusion, but now how does this work as a point towards your non-full sequence diffusion?
non-full sequence. I see. We will see the particular case later. It will also work on full sequence, but as we will see later, and also like in our paper, like we are just doing it better. Yeah.
Okay.
Yeah.
So
In
I
fact,
think the point of this slide is just to say like this is a property that diffusion models uniquely have, as opposed to, you know, if you do next token prediction, like diffusion models, you can bias sampling, you can like basically do planning via guidance, via classifier guidance. This is like this is something that people like about diffusion models. That's the whole point. So like if you have a diffusion model, you can bias it via guidance. This is something people appreciate about them. And I mean, in you know, in LLMs, you can do like search, right? You can basically do search, but they don't have the same way of doing planning via classifier guidance. This is the whole point.
yeah. So
I
that
see.
is how will you like use each type of model like to do planning overall?
I think I would say that with only autoregressive models, you can also the search, of course, we can do like some beam search stuff and things like that. But I think you can also do stuff like tilting your distribution with something like plug and play language models, so the PPLM, and then you can use like a classifier to tilt your distribution, or you can yeah, there was recently this paper on just using a classifier on the logits and then biasing the logits toward like some RLHF data. So yeah, I would say that maybe with the next token prediction, we can also do guidance. But maybe not as good as if we have like a longer horizon that we're generating at the same time.
Yeah, I think there are some guidance efforts like from language model as well. However, like I imagine like many of like those people, like what they do is like they do guidance on the next token only. That is like when you predict the distribution of like next token, like you can bias it towards a particular like thing or like next few. But like if you think about this, like language models, like when they generate next token, they need all the previous tokens to be like fully determined, right? That is
Yeah,
what we call it, next token prediction.
the best
Everything
paper, yeah, the best paper award at ICML was also something where they like train a value function to given the current sequence and yeah, given the current sequence and the next token, assign a value of the final sentence to the next token. So basically turn the sequence generation into maybe sort of an RL problem and train this value function that tries to take in the whole sequence into account before the whole thing has been generated, or try to take the value at the end of generation into account, and yeah, then do guidance like this. But anyway, I think now I get the point, and probably anyone else also gets the point of what you wanted to say on this slide. Like there's guidance, there's rollout and search with diffusion models, guidance very obvious, with language model or next token prediction, search is very obvious. And now maybe with diffusion forcing, we can get the best of both worlds, even if we maybe can also do guidance with next token prediction. It's might be easier and it might be better to do it with diffusion forcing.
Yeah. Okay. Check the time. Okay, we have enough time. So what we want here is that like first of all, we want the guidance ability from diffusion models. And in particular, we want to do sequence level guidance, which is something teacher forcing and next token models cannot do. On the other hand, we also want like compositionality like from next token models. That is, for example, like you have a training set that is like working diagonally. And what we want is that like sometimes people have this prior about like how Markovian the task is. That is like your what you want to do next only depend on your current like observation, like independent of like everything in the past. Okay, and like that's often reflected as a like the thing here that is like you can go to the middle first and then you turn around. That is like you turn around because like now you're at the middle and like you know that you can be memoryless to take the next action. And like full sequence diffusion model, like they have a fixed horizon. And as a result, like what they do is like you have little compositionality at sub trajectory level. That is, if you want to do compositionality like below the token length it's trained on, like it's really struggles. On the other hand, this is quite easy for autoregressive or next token models. You just need to like tell it you are memoryless, discard all the memory away. Then you can like do something in the middle. So we want compositionality here. That is the ability of like teacher forcing like or next token models. And also what we want is that like we want causal uncertainty. That is in full sequence diffusion, you can see that like let me click the video. So this is from some prior papers. You can see that when we gradually diffuse it, like throughout the trajectory, at the end of the very beginning, like they are of a similar like uncertainty level at planning. However, like when we humans are planning things, what do we do? Like we kind of have an idea of what's going to happen in the near future, but for the far future, it's going to be very, very uncertain for us because it's such a wild distribution, right? And why is that? That is because every time step we step into the future, it's a complicated distribution, and there are naturally like uncertainty that accumulates throughout time. Okay, so here if I say I want to reach a goal as soon as possible or something like that, like will be really interesting. Like if we can like think about like plan like what human does. That is, I always start from this goal. I don't know what's going to happen in the future. Like but however, like I can do this guidance planning like with causal uncertainty, like with the future uncertain. Okay, so for example, in this particular visualization, they have to enforce that in your last time step, like you end at this goal. But however, like what we can have is like we want to reach the goal as soon as possible, instead of like just stepping at the end. So in this trajectory. and we can leave like a lot of things open-ended, like as we plan and progress. And you will see that like why is that beneficial later. So that is causal uncertainty here. And finally, like we also want flexible horizon of the models, and that's all. That's trivially from the fact that like if you train a causal model, like you can just like roll it out like for one token, like or next few tokens, like it's all fine. Yeah. So, and what is a highlight of diffusion forcing? So if you talk about like full sequence diffusion models, remember that we add same level of noise to every single frame. And however, in diffusion forcing, the core idea is that you just add different level of noise to different frames because noise is just levels of masking. And because language models and all those kind of models can handle masking and use that a nice pre-training objective, you can also do that like with diffusion by masking tokens out at different noise levels. And in fact, by doing so, you will see a lot of benefits later. That is, for example, you want to execute it as like you can execute sampling in many different ways. If you want to just diffuse next token, like you can just like feed it with clean images, clean context before, and gradually diffuse the next one, or you can like do full sequence diffusion here. Yeah, Hannes, what's your question?
What does adding a little bit of noise mean in the context of discrete data, like text?
I think there are independent line of research like about like how to use like diffusion like for language models. I think adding a little bit of noise to discrete data, like of course, like if you have like one hot embeddings of like discrete data, then adding noise is just weird, right? Because like if you discrete and you're represented by one hot embeddings, then it doesn't form a nice and smooth manifold. However, nowadays when people train discrete models, what people do is like I have an embedding layer that kind of embedding like this like one hot encodings like into like into more complicated representations, and though many of those representations form a smoother manifold, then like you are kind of like perturbing on the manifold only. On the other hand, like there are people like who just like add perturbations like to logits. That is, before your softmax is like logits that get mapped eventually get mapped to a distribution, and you can view like adding perturbations to logits as like perturbation to the distribution as well. Although I would say that is something different from diffusion because it breaks the many mass of diffusion.
Well, okay, then I would say what you're talking about now are like continuous space diffusion models for discrete data sequences. And then there are, let's say, discrete space or categorical space diffusion models for categorical or discrete data. And in the latter one, people do things like changing tokens to random other tokens, like one category to another category, and or just masking out something. Like you have a token and it turns into a mask token. And now if we, like what you talked about, these continuous space diffusion models for discrete data, they are, it's quite clear what it means to add a little bit of noise. But then if we're using these diffusion models that rely on, for example, masking, or still always staying in a space of a valid sequence, even if the sequence is noised, like where noise is not added to a single token, but to the sequence, would you say that then there your framework doesn't apply?
I would say diffusion like for discrete sequence is like a orthogonal problem like to what we are doing here. Like our entire paper is about continuous data because that's the most nature domain like for diffusion. I would say like if we combine our method probably with some specialized techniques that's using diffusion like for discrete data, like maybe it will work too.
Yeah.
But
Okay.
it's just parallel. Yeah.
Yeah,
And
but
I
I
think
think
go ahead.
the frameworks that work the best right now for or diffusion models for discrete data are things like Andrew flow matching or score entropy discrete diffusion. They do not use this continuous space framework for discrete sequence generation. So probably for text stuff. Yeah, anyway, just noting that. But Vincent, what did you want to say?
Yeah, I just wanted to call out there's two related or concurrent papers. One is called Simple and Effective Mass Diffusion Language Models, where they look at, this is from colleagues at Cornell Tech, where they look at diffusion. And I think, I actually haven't read the paper, but I think it is actually investigating the question for language. And language would be an example of a discrete sequence, correct?
Yeah.
And I think for, in that paper, they find performance that is quite competitive with non-diffusion autoregressive models. So with just next token prediction. But yeah.
The comparison I'm making is not between autoregressive or any other autoregressive and diffusion model. I'm making a comparison between two types of diffusion models for discrete data. And one diffusion model basically embeds discrete sequences in a continuous space and then runs the diffusion in this continuous space. And the other type of diffusion model always stays with a discrete sequence and just changes tokens of the sequences, noise injection. So in the second type, there is no notion of adding and like having more
like
or
small
less
amount of noise,
for a single, yes. So one token is either fully masked or full noise or no noise in most of these frameworks. And this includes the two frameworks that I now would think are the best for discrete sequences, which is Andrew flow matching and the score entropy discrete diffusion from.
Have people looked at those for language models then?
Yep. So there's in score entropy discrete diffusion in the paper itself. It's also a best paper award at ICML actually. There they compare with some language models, and in a paper that came out very recently, from Yaron Lipman and Meta people et al. It's literally called discrete flow matching, the title of the paper. There they compare with some, they compare with SET as well, and do text experiments. Anyway, I think let's continue talking about the continuous space diffusion models, because that's what we're dealing with here. And then maybe the papers that are more relevant and we can talk about for context this rolling diffusion and stuff like that.
Yeah. So in diffusion forcing, like you can train models at like different noise levels. It still works. And at sampling time, what you can do is like now you don't need to like diffuse every single token at the same noise level. For example, like you can first fully diffuse the first token, leave the second token like slightly uncertain during the process, and fully diffuse the third token, and something like that. And it's not mandatory that they stay at the same level as at prediction time. And you can imagine that you use this for many different cases. So for example, next we will discuss what does this buy you, and you will see the specific examples. So first of all, here are some failure modes of just doing t-shirt forcing and next token prediction. So that is once you make some slightly errors, there's no way to recover, and it can blow up. Why is this? Because at training time, t-shirt forcing is assuming that all of your context frames are clean ground truths from your data set. However, at sampling time, instead of feeding it with ground truth context, what you are actually doing is that you make your best effort to generate a next token and feed it into concatenate with the context and tell the model, my newly generated frame is ground truth, just predict the next token for me. However, that has an issue known as compounding error here. So what about full sequence diffusion? So if you look at this Minecraft videos here, what you realize is that like you can generate really nice videos like with diffusion forcing here. However, like full sequence diffusion model have some kind of inconsistency. So if you look at this, so sorry. So by the way, this Minecraft video is action conditioned. So like it's actually, so if you look at this, sorry, I need one moment to find my mouse. Okay, if you look at the ground truth images, you can see there is this tree on the upper right corner of the the frame 10 of ground truth. Okay, that is the same tree as the frame 25 of ground truth that you are seeing in the middle. That is the same tree. And when we do action conditioning, like when you, so basically the action drives the agent walk forward and turn right, it's supposed to see that tree. Okay, it's the same tree. And like you can see like diffusion forcing actually maintains a really good level of consistency. And here, like I think the intuitive reason is that like by doing this like noise as masking schemes, I'm saying that like you should like look at every frame, like when you're doing denoising, rather than like you just focus on like the frame immediately before the frame like you are denoising, or like on the other hand, like you should, if your first frame is clean and ground truth, you should fully trust it. Don't treat it as noisy like full sequence diffusion models. Okay, and you can see like full sequence diffusion models is just like slightly it's just less consistent here. And on the other hand, there is also this nice capability that's related to consistency. So for those who have some background like in video diffusion, you'll realize that what people typically do to do conditioning on past frames is this. You first train a full sequence diffusion model like Sora, okay? Let's say like with a context length of 100, okay? And at test time, if you have some history of 50 frames already, what do you do to predict the next 50 frame only conditional on the first 50 that's already given? What people typically do is that, okay, now I throw my 100 token diffusion model at my data. However, instead of starting from pure noise, what I'm going to start with is the first 50 frames concatenated with 50 frames of pure noise. I throw my model at it, denoise it, and then whatever the denoising outcome is, I replace the first 50 with a ground truth context again, and then diffuse. Then I replace it again, and I diffuse. Then I replace it again, and I diffuse. Okay, so what happens is that at every single iteration, what is the first 50 frames sees is clean. However, at training time, you are telling it that at this noise level, your first 50 frames and later 50 frames are of the same noise level, right? And so there are some weird inconsistency that could happen, which is addressed in Jonathan Ho's very first like video diffusion models. And he called this technique called conditioning by replacement. And then he also proposed a technique to do it that is called reconstruction guidance. Basically, like I just add a guidance term to my diffusion process such that whatever I diffuse, I have to make sure that the next prediction like has first 50 frames aligned with my ground truth 50 frames. And that process is actually expensive. You need to take the loss and like do a backward propagation. And in diffusion models, generation is already very expensive. You don't want to have an extra backward propagation just to maintain your consistency here, right? And diffusion forcing actually allows you to get rid of that, because what it does is that at training time, it already sees samples where the first 50 frames is ground truth and later 50 frames is what you are currently diffusing, right? Then at test time, when you actually do this conditioning here, you can explicitly tell him that your first 50 frames is already clean, and you can fully trust those. And we can just do very nice conditioning, very consistent stuff without this reconstruction guidance that's really expensive. So is everybody on the same page with me?
Yeah.
Okay, let me. Sorry, let me look at some questions, but I can't find my mouse, which is, okay, I found my mouse. If noise is impact, how do you guarantee the spatial pixel consistency? So about spatial pixel consistency of the samples. I mean, when you are generating next frames, like it does see every single, like when it's graduating, when it's gradually diffusing everything, like it does see all the pixel around it. So I think it works because diffusion model works, because it just look at the whole image. How is the sampling speed? Oh, it really depends on like how do you sample. So when we do this, like if you do autoregress sampling, it will be like really, really slow, right? Maybe you can accelerate with KV caching or something like that. However, you can actually also sample like with other schemes, like for example, what we call like pyramid sampling, or like we can just do full sequence diffusion. And like we can sample that really fast, like actually on our like 3D unit implementation. Our original like RN implementation is slightly slow. And okay, on the other hand, this is not in the original paper, but like we are already like working with latent diffusion, and we can generate really nice high resolution videos. This is 512 by 512 with diffusion forcing, and we will have many more higher quality results coming from diffusion forcing V2, which we'll like have in the future. We're actually working on that. Okay, as a summary, like okay, so there is another ability like what diffusion forcing can do. So you know that when people do autoregress sampling, as I said earlier, like you will see this compounding error. Why is this? Because at training time, you assume all your context is clean and nice like ground truth. But at sampling time, you feed like your generated frames to it, and it contains like uncertainties that should not be treated as ground truth. However, with diffusion forcing, what you can do is like you can stabilize this, or you can tell it that, I'm now feeding you not only ground truth, but also like this frame is generated and it may be slightly imperfect, slightly noisy. I just tell it, my generated frame is of like noise level of like 30 or something. And then like it incorporates that information into the generation. And I do not fully trust it. I fully trust the context. I don't fully trust the image I just generated earlier. And by doing that technique, we can ask it to like roll out really long. Like in the original RN implementation of diffusion forcing, we can roll out like 2,000 frames. We are also actively working on that like in latent space as well. And you can see that like this is from our original paper. Like you can generate. So we train this model on like 50 tokens or something, and then like we can roll it out for like 1,000 frames. On 1,000 frames, and like it just remains legit without like blowing up quickly like autoregressive sampling. So what you are seeing here is autoregressive sampling, like similar to teacher forcing. However, because we trained with diffusion forcing, not teacher forcing, like it's able to do this. What's more remarkable is that in the original RM version, this video you are seeing here is without sliding window. So that is, it's somewhat like a quite out the distribution, right? Like because usually people do generation, you need to after you generate some frames, you need to reinitialize like your initial token, like Z0, like telling it, I'm generating a new sequence, just start from here. Without sliding window, it's really hard because like you are rolling a longer and it's not trained on. And another ability of diffusion forcing is that you can like do planning with causal uncertainty and like a full trajectory guidance. So what does that do is like, of course, like you can do like a maze planning as we all have seen before. But here, like if you look at this, what you can see here is like I can diffuse the first like initial parts of the trajectory more and leave the future uncertain. And this is quite important, like in many stochastic like reinforcement learning settings. And compared to prior works, what does this allow us to do? Oh, by the way, this is causal, so it enforces kind of causal, a lot of like causal property. That is, in many prior papers, they just diffuse the trajectory. But if they jointly diffuse the actions, they cannot actually take the actions. They have to throw the actions away and just like follow the trajectory. What we do is actually we can actually, yeah.
Yeah, and like we also have some questions in the chat regarding this, but can we talk a little bit more about the method itself again and your training procedure? If you go to those slides.
Yeah, I'm reading the question. The RM weight theta maintains latency capturing the infinite. Yes, so in our original paper, like the algorithm is trained with RN because it's heavily inspired by Bayesian filters and like has nice mathematical explanations. I also like RN like for decision making. However, it works on transformer. It works on like any like sequence model like you can imagine. We already tried ourselves on 3D unit and temporal attention. It works very well. In fact, like the videos like you see here are with like temporal attention that is like a transformer layer.
Yeah. But I think it's all a little bit abstract how you actually now train the model and use it during inference. Can you just go over the training procedure?
Okay, yeah.
in steps and the inference procedure. Yeah.
So
Yeah.
at training time, what do you do? Now you have a sequence that is like now you have a sequence. What you do is like you add independent of noise to every single token. You throw it at your diffusion model and train it with exact the same objectives that you how train different models.
Okay, so
Okay.
there's no why don't we like have a schedule where the beginning is maybe less noisy than the end?
You can also do that. In fact, in our like follow-up paper, like we are already exploring some of that perspective. However, we found that like so in our original paper, like we think this masking is just really it's really simple. Like you just add in independent noise level, right? And like although there are some temporal correlation like in video projections that like you should always look at your immediate previous frame like more. However, when you model generic sequence data like and want to discover like complicated dependencies, like you have no priors about anything yet. So what we do is we just train independent with independent noise.
So maybe just to add to this, like one way to think about it is that, imagine that at test time there is lots of, at inference time there's lots of different sampling schemes that make sense. So for instance, we talked about this idea of causal uncertainty. So like even a little bit of uncertainty in the next time step can mean a lot of uncertainty in the far future. But there is lots of other, like there's lots of sampling schemes that might make sense at test time. So if you already know exactly what sample scheme you want to use, then you might say, or maybe then it makes sense to train with a specific one. But it turns out even that isn't true. But the key insight is that diffusion forcing is kind of at training time, you're kind of training in the model to be compatible with any sampling scheme. So by basically independently choosing the noise levels at every time step, at test time, you can choose whichever sampling scheme you want to use. So if you want to use a sampling scheme where uncertainty is increasing over time, then you can do that. Imagine, however, for instance, you want to do frame interpolation. If you want to do frame interpolation, I have frame 1 and I have frame 100, right? And now I want to generate the 98 frames in between. Then the case that you have is you basically have zero noise for frame 0. You have zero noise for frame 99. And now you want to basically diffuse all intermediate frames. So this is actually a different example for another kind of sampling that you want to use. Or if you have guidance, or like imagine you have like a different lengths of history, or you have this thing that Boyuan talked about, like you have a Markovian assumption. So basically, by varying the noise level independently, you're basically training the model for every possible sampling scheme.
Well, yeah, but if the sequence gets a bit long, then we are also training it for like no sampling scheme very well, because it's just so unlikely that we ever see something that is similar to what we use as a sampling scheme during training.
Sure, yeah, I think that's fair. So you're saying that, well, maybe are we wasting capacity? Is I think what you're saying, right?
Yeah, and to the extent that there's no capacity left for the for what we're training for, because it's like this combinatorial space of noise possibilities. And if we now have a sequence length of 100, then the chance that we have noise that is monotonically increasing, for example, is very, very low.
I think theoretically it's possible. However, like actually, like when we do our temporal attention like experiments, actually it didn't empirically happen. The training is actually really efficient. We didn't notice much like loss like redundancy in training. Not redundancy, but like a significant slowdown in training when we actually do our experiments. Yeah.
But I actually find it kind of surprising that it works to train with like something where your training distribution is so different from what you have during inference. And there have also been other papers like this. I forget the name now, but there's one that for every pixel in an image adds a random amount of noise instead of adding the same amount of noise to every pixel in an image when generating it. And now you're essentially doing the same with instead of pixels in an image, you have frames in a video, so to say, or frames in a sequence. Yeah, also, this is sort of reminiscent to me of any order autoregressive models, right? Where you just train with, or you do autoregressive generation, so to say, or you can also interpret it as a diffusion model, where you just take your sequence, you have a probability for each token to be masked or unmasked, and then and this probability is something between 0 and 1, and it's the same for every token. And then you mask it or you don't mask it. And then you can generate in any order at inference time, right? Then you can do something like generate the next token that you unmask at inference time is the one with the least amount of entropy or something like that.
I have I think like one thing we realize is that people actually want to condition test time like in many ways. Like right now, you can see like a lot of people are doing keyframing, right? Like from Luma, like they are, and many other like video gen companies. They want this keyframing like ability. That is, I condition not only condition on first frame, but probably many like random frames in the middle, right? I think like diffusion forcing, like why it contains some redundancy. I think this redundancy is actually what people needed in the diffusion in the video diffusion models. And I think just conditional like and if you just do full sequence diffusion, it had never seen the examples where like your first frame is like clean, your this keyframe, the 10th keyframe is clean. Like it had never seen that before. And I think this kind of redundancy, while like making it more could be more expensive, it's actually necessary.
Mm-hmm.
And actually, I think, Hannes, I will say that I share your surprise. I think your surprise is I agree with your, I think it is surprising. I would totally agree with this. And I think, I suspect that there might be something else at work. So, that there is, so, we are kind of, there's, of course, this perspective of saying you're training your model for every possible sampling scheme, but there is potentially this other notion by which you can also think about it as augmenting your training data, right? Like if you fix your training sequence length, if you're like masking out the first half and then you have like, let's say frame 50, like the same sequence length with 100. Now, the first 50 frames randomly happen to be like have high noise values, but the 50th frame is actually clean, and now you're predicting the other frames from the 50th frame onward, for instance. It is also a form of just data augmentation. So you just get more, yeah. So I guess there might be other effects at work other than just like training for all possible sampling schemes that might maybe explain why the model isn't training any slower.
Yeah.
There is a question in the chat. How do you find temporal independent noise training would work? I wonder if there are any intuition about it. What's an empirical result? Actually, I think I have very good intuitions about why they work. First of all, in language models, masking out entries works, right? And people have tried that same thing on video models. Like you just mask out some frames or like part of the image like something and try to predict it from the rest. For example, like MAE is like masking out some pixels and like predicting that from the rest. However, what will happen is that your model will predict the very blurry images on those like mask out entries. And that's very low frequency like information about the image. And diffusion is exactly the way like to do that. Maybe because you have this intrinsic uncertainty, applying an L2 loss will force you to like predict the blurry parts of those like masked out entries. However, with diffusion, like you are kind of like breaking down this complicated distribution into small ones. And then like you can get high frequency, capture the high frequency parts as well. So that is a core intuition there, like by training with independent noise and like why it should work. Okay, and finally, like we also have like this little robot experiment. I think we are almost out of time, but like basically in this thing, like what we are trying to do is that we are trying to do long horizon imitation learning that is also a sequence model. And the task here is we just swap these two fruits using a third slot. And this actually a traditionally hard task. We tried some prior like behavior cloning like baselines in robotics. Like if you do robotics, you will know this. However, most of them rely on the fact that things are being Markovian and they don't have memory, they cannot do this long horizon. And like what we're doing here is like we collect a lot of demonstrations, we train sequence generation models on it, and like we can execute this. What's more remarkably, because diffusion forcing is trained on noisy context as well, I can add perturbation like to the observation. I can just throw a target back into the image, and like it's a strong distractor. It's out of distribution. But however, like you can just let a prompt the model that your observation should be treated as imperfect. It's noisy, so you should like don't treat it as ground truth, treat it as like something noisy, and like it's able to complete the task like by prompting it to do something like that. So as you can see, it's like the like independent noise level every token thing is really powerful depending on how do you want to use it. I think this is just the first paper we were trying to get. And we'll have a lot of like awesome follow-ups coming up very soon, and we are actively implementing it like with latent diffusion, like a really nice high resolution videos, and many other things. I think in our next paper, I can promise you the video result is going to be much stronger, and you will see the true power of diffusion forcing very soon. And here is a team I would like to thank both of my advisors and awesome collaborators.
Okay, thank you. So video generation is the main thing that you're interested in. Is that right?
I want to solve video generation first and then like do it on robotics.
Okay.
Yeah.
Denise, what's your question?
Yes, thank you for a great talk. Two questions. First, just a very simple one. For the experiments on the maze prediction, you are training the model for each maze separately. Just out of curiosity, how long does it take to train? And essentially, like, how in a realistic environment, how can you adapt to a new environment, sort of in context? This is the first question, and the second is
Yeah, let's go with the first
again
one.
about noise scheduling.
Denise, let's
Okay.
go with the first question. Boyuan?
Yeah. Yeah, we are training a maze independently because this is a standard benchmark, and like the data set is like per maze. Okay, and it is indeed a bit slow, like in our first version when we train with RN. However, recently I just implemented the transformer version of it, and to my surprise, it's actually much faster than RN. Probably because people optimize transformer kernels so well, and like I can just train it like a really fast, like 30 minutes to 1 hour, and it does this kind of planning really well. And to apply to real world, like actually, in real world, people seldom do state space planning like this. Like people's observation is always complicated, like visual motor policy that is you always have camera images as your observation, and I imagine that if you actually train it with you train per task, it's actually quite inefficient. Because why don't you just train a giant model that knows everything, like has all the physics knowledge in its mind, and like you can do ChatGPT style like search policy, like that kind of thing, like with that kind of model as well. So I think like it's inefficient if you train it per task, but if you just mix everything together and train a word model, like your efficiency per parameter like will be much higher.
Mm-hmm. And the second question, so is it true that during inference and probably during training, you have a fixed noise scheduling? So you have this matrix M by T, where I believe T is a sequence length, and M is number of noise levels, or vice versa. And my question is, this matrix is not learnable, or is it? I mean, can the model learn how to assign noise itself?
How to assign
guess-
noise itself?
Sorry?
I see. I think that is a good question. Right now, our sampling scheme like largely depends on the manually designed noise schedule. I don't know. I think like I like that controllability as a human because I have this manual prior, but that kind of manual prior is really something that like you need to like some like a high intelligence like creature have to design. Like for example, maybe in the
Yeah.
future you can ask the ChatGPT
Yeah,
to like
the reason.
Yeah.
I was
We actually-
mostly asking because I was kind of interesting at how this kind of model can be applied to something like ARC challenge. If you know this challenge where you essentially need to solve this kind of IQ style logical tasks on a grid, and essentially you need to generate a grid that has some compositional structure, sort of consistent with a few examples. And yeah, you obviously can do this autoregressively, but then ideally you probably need to go over the whole grid a bunch of times. And I was thinking that maybe this style of generation, it can perhaps be used to sort of go over the grid multiple times, updating the tokens and maybe looking at what you get. As you say, you can apply Monte Carlo decision making. So essentially it's diffusion plus Monte Carlo tree search of the whole state space.
Yeah.
But then I think you need to somehow, I don't think that you can use fixed noise scheduling. It seems that for this kind of inductive reasoning, you need something much more general, but I don't know how one would even start thinking about.
Yeah, I think, yeah, I think that is true. Especially in decision making, there are many kind of like factors that influence how you do want to like do this thing. For example, certain tasks just don't care about causal uncertainty as like anyway, and there are certain tasks that has strongly dependency. Like also sometimes your environment is deterministic, sometimes your environment is just very like have a very chaotic distribution, and there are many schemes. I would say like it will be interesting to explore that in future work. I don't currently have a plan for it right now. We just like manually design the denoising schedule, and I think that's what a lot of people did.
Okay, thank you.
All right.
Yeah.
Yeah. If you want to read out the question loud, then that would be nice.
If you assume the states to be Markovian so that you have input sequences of length 1, would diffusion forcing amount to adding noise to the input during training?
I'm not sure what's meant with that, but like if the data really is Markovian, and we have like if the data is Markovian, right, then your method shouldn't help if the model does everything right, so to say. But if there's like some mistakes in what the model does, then some looking back and being able to correct mistakes during rollout might be helpful. I'm not sure.
I think in the Markovian case, it could be like that. Because you are rarely out of distribution, like in terms of your conditioning variable. But if in the non-Markovian case, like for example, you make some mistakes and you have to condition on like the outcome of that mistake, for example, it's making the context very out of distribution, then like having this kind of noise would be very nice.
Yeah.
Although like I'm not exactly sure like if I interpret the question from Harris correctly.
Same. But then also like one question that I've agreed with or that I also had, you said that you can tell the model that the previous frames are self-generated. How did you do that?
So you don't tell it is self-generated. Instead, you can say condition on that with caution. Don't condition it as ground truth. Instead, condition it as noisy.
Yeah.
So because we feed retrain it with independent noise level everywhere, right? It's like for some token, you can tell it has noise level of not zero, but something slightly higher. It contains some information, but the information is not perfect. Code is available online on GitHub. We have two code bases now. It will be three. So the first one is our original release code base. But later on, because it's very popular in generative AI community, I decided I should not hide everything to myself for next project. So we also released the 3D UNet and transform and temporal attention version that is much better for videos. I will also release the transformer implementation for maze planning very soon. It also has much better performance and much faster speed. However, I'm also kept some code to myself. So everything about original paper is reproducible and it's open source. However, I also kept some So some results here are with latent diffusion and with some proprietary techniques. I'm keeping those techniques to myself until the next project. But in the next project, those will be open source soon because they have much stronger result.
Nice. Okay, well then, I would about call it a day here. Is there any last things you want to say?
Yeah, I'm glad that you host this, and I'm happy that people have a lot of questions and interest about the project. I think there are a lot of potentials about this project. Just check out our app website. I actually listed out a lot of like potential follow-ups people can do with diffusion forcing, and I'm also actively maintaining the code base. If you have questions, just raise a GitHub issue or send me an email.